Good afternoon, my name is Ivan. I'm from Brno University of Technology, and I would like to present you the SmartOTPs, which is the first one-time password scheme for the blockchains. This is a joint work with Dominic and Andre, who are also from BUT, Peter from University of Twente, and Alex with Pavel from SUTD, where I was doing postdoc before. Our motivation for our work is to make a Google Authenticator for the blockchains, which would provide short enough OTPs that could be transferred by the mnemonic words or by small QR code. So we analyzed the options for the OTPs and we found out that OTPs don't provide non-repudiation. Therefore, they might be misused, intercepted and misused in the context of the blockchain. As a consequence, we argue that we require a two-stage protocol where in the first stage, user publishes the operation that is signed by his private key, and in the second stage, he confirms the operation by the OTP that is linked with the operation. We specified requirements on the general OTPs. OTP must be authentic since it must be binded to a user's wallet. A particular operation must be linked to a particular OTP, which is the linkage, and two different OTPs must be independent, so one OTP cannot be derived from the other one. We also specify requirements on air-gap OTPs, which are on top of the previous one, also require short length of OTPs. So, if you would like to use a conventional means for implementing OTPs like asymmetric cryptography, it would impose a long size of OTPs, which might not be usable for the users to transcribe the words. Symmetric cryptographic construct would provide short OTPs, but the problem is they have a shared secret. And Lamport hash chains don't have a shared secret, and their length is also very short, but they don't meet the requirement on the independence of OTP, since one OTP can be derived from the other one in the chain. Therefore, we propose SmartOTPs, which are based on a smart contract for implementation of the two-stage protocol, and on a pseudo-random function for the generation of OTPs, and Merkle trees with hash chain for their aggregation. We have three entities: Authenticator, which is a smartphone or hardware device providing OTPs, client, which connects the private key wallet of the user, and the blockchain, which stores integrity information associated with these two factors. Base version of the SmartOTPs has only OTPs aggregated by the Merkle tree. There are no hash chains. So verification that smart contract needs OTP and its proof to derive the root hash. But the problem is that the proof mustn't be transferred from the authenticator, but it can be stored at the client in its cache. And whenever the user submits the transaction to the blockchain, the proof is provided from the client, not from the authenticator. Hence, the authenticator can be air-gapped and user transfers only the OTP itself. So, this is our two-stage protocol, where in the first stage, user initiates the operation by inputting the parameters of the operation, let them sign in the private key wallet, where he confirms the data on a display, and then this transaction is sent to the blockchain, where the signature is verified and object for a new operation is stored. In the second stage, user inputs the ID of the operation to the authenticator and gets the OTP. Client fetches the proof or the authentication path from its storage, append them to the transaction, and send the transaction to the blockchain, which verifies that the operation is pending, verify the OTP and the association of the OTP with the operation. Afterwards, it executes the operation. However, the base version has some problems. For example, a limited number of OTPs, which has usability and security consequences, since the OTPs can be depleted, or the attacker might block these OTPs by depleting them. So, if you would like to increase OTPs naively, it would have some requirements on the client storage. Client would need to store more nodes of the OTPs. For example, if you would assume the tree with 2 to 32 OTPs, then client would have to store 130 gigabytes, which is too much. For example, if user would have more wallets, it would be just unfeasible. So the solution are the hash chains, which can be appended to the marker tree, and they can be iterated layer by layer. So they multiply the number of the OTPs by the length of the chain. The same configuration would require a client to store only 33 megabytes of the data, assuming the hash chain which has 4K of layers. Another problem is that OTPs can be once depleted even with this hash chain. So we need an operation to update the root hash of the tree. And we argue that the operation or the protocol for the operation where there's two stages cannot be used because the attacker can block the funds of the wallet. The attacker who possesses the private key. So as a solution, we propose three-stage protocol which requires two append-only lists. We state this protocol in our paper and I will not deal with it here due to the time limitation. Next, we made this cost and security optimization of our scheme, since executing smart contract requires some cost. So smart contract can actually store only particular layer of the nodes of the marker tree instead of storing the root hash, and the verifications of OTPs can be done against this layer. But these have to be viewed as a trade-off, since storing data at the blockchain is costly, and the second variable of this trade-off is the benefit brings by the caching. We empirically find out that the most optimal setting is to cache the layer which has depth height of the tree minus 3. Problems of the caching are that it requires prepayment for the storage of all these nodes. And after depleting the first iteration layer, the security of our scheme is decreased by the logarithms from the number of leaves in the tree or the number of the hash chains, which is not negligible if there are too many hash chains. So as a solution, we propose partitioning to subtrees, and therefore we have more trees, and after depleting the OTPs of one tree, we introduce a new subtree which requires a new operation. But the prepayment is made only for the cache layer of the particular subtree. This is how looks the full version of the SmartOTPs. We can see that the last OTP of one subtree is used to introduce the next subtree or its cached layer, and the last OTP of the parent tree is used to introduce the new parent tree, including its first subtree. We made a security analysis, assuming the random oracle model with lambda bits, and if we take only one hash chain, using the Kogan et al., we need lambda plus 2 bits to achieve the security as strong as lambda bit oracle. If we would assume hash chain without subtrees, so the SmartOTP scheme with hash chain but no subtrees, then to achieve security of our scheme equal to lambda bit oracle, we would need the same amount of bit as before plus logarithm from the number of hash chains or the number of leaves in the tree. If the tree is too big, this might have a security drop quite high. Therefore, we argue that subtrees help to improve this problem, since they assume only the number of the hash chain within the one subtree, which can be, for example, 64. Therefore, the security decrease is not as significant as we wouldn't have a subtrees. On top of this, we assume the attacker who want to conduct unauthorized operation and render the wallet unusable. It has a full network access. It can intercept and override users' transaction with higher fees. This is also known as transaction front running. We assume three types of exclusively occurring attackers. One has access to wallet, second can tamper with the client and thus deceive the user, and the third one has access to the authenticator. We showed in our paper that our scheme can resist to all of these three attackers occurred exclusively. Our scheme has also other properties. It requires user to wait on enough block confirmation after the first stage of the protocol. Otherwise, the attacker possessing private key may hijack the OTP and reuse it for his operation. Our scheme is more convenient for the blockchain with fast time to finality when there is no need to wait for such number of confirmation. We also evaluated resistance of our schemes against the quantum attack using the Groover's algorithm with realistic assumption from related work, and we found out that we achieve 98 bits of post-quantum security for OTPs that are 128 bits long. If we would like to achieve 120 bits post-quantum security, then we would need OTPs that have 205 bits. We implemented our scheme using the Ethereum and Solidity for smart contract, JavaScript and DApp for the client, Android application for software version of Authenticator, and Node MCU for the hardware version of Authenticator, including some cheap display and keypad. Here we can see how this display shows mnemonic words of one OTP or QR code of version 1. On the right side, we can see the client interface and Android application providing the OTP through the camera. Trezor is used for the first stage of the protocol where the operation is initiated. We made a cost analysis of our scheme, and regarding the deployment cost, we can deploy the smart contract maximally up to caching layer which has depth maximally 7. After introducing a new subtree, we also need to prepay for a caching layer of that subtree. So this is depicted in this figure on the right side, where we can see that this is significantly cheaper in contrast to introducing the cache layer of depth 7 here during the deployment, where 1 million gas is somewhere here, while we require much more if it is introduced during the deployment. So the storage is more efficient to occupy during the lifetime of the smart contract. On the left side, we can see the average total cost per transfer operation, which means that the deployment costs are already included into the overall cost per operation for different configurations of 3, and we see that the price as the time of writing was around $0.15. Including the hash chains, we can achieve the savings from 12 to 20%. In the middle picture, we depict the configuration with a depth of the cache layer equal to the 7. On the other side, there is unlimited depth of the cache layer, and on the right side, there is no caching. So hashes also bring some improvement in terms of cost. Finally, I discussed some usability issues and implication. We argue that SmartOTPs has several usability characteristics as state-of-the-art solution. What is extra is the operation for introduction of a new subtree and parent tree. However, these occur only after 32,000 of OTPs or 33 million OTPs, depending on the configuration. Also, the input of the operation ID into the authenticator might have not interesting usability characteristic for the user, and therefore we suggest to reset this counter after passing the first iteration layer of particular subtree, which can be as small as 64. Also, we counted the number of the elementary actions for the SmartOTPs and for the Gnosis, and we found out that SmartOTPs was a bit better. We also made a cost analysis where SmartOTPs achieved similar cost as other multi-factor smart contract solutions. However, let's emphasize that Trezor multisig is using just one transaction, while we are using two transactions. Gnosis is using two transactions to do the two-factor authentication. We also have functionality for the lost secrets, where user can recover even from such state. And finally, we found some vulnerabilities in Trezor wallets, which display only 8 bytes and 16 bytes of smart contract parameters, so user has no way to verify other data in this transaction. We reported this to Satoshi Lab, and as a mitigation, we propose to bring the most security critical parameter at the first place so user can see it and verify it. So that's all. Thank you for your attention, and if you have any question, I'm happy to answer them.